The gamma factor is a cornerstone of special relativity, and we're going to talk about another way to derive it here in this video. The derivation is called the LightClock derivation, and it's a simple thought experiment, and it's a really cool way to think about how time and space have to vary if we accept that the speed of light is constant. And so the thought experiment involves two mirrors, and those are the horizontal lines you see, and the dot there with the square around it, that is a photon. And what happens is the photon bounces between the two mirrors, and that is how we can record time. There's some kind of computer on here that marks a tick, and then a tock, and then a tick, and a tock. And so we have this fancy light clock, and by using it, we can measure the passage of time. So, what will a light clock look like that's moving past us? We'll say on a train. So I created this cool little flip book here, cool little 12 frame per second animation, and that's what we will see, a photon moving from left to right across us. So that is the motion we see from a moving reference frame. And what does that look like? We're going to write everything in terms of distance. So we have, and in terms of distance I mean velocity times time, because velocity times time does equal distance. But how fast is the particle moving here? Well, we know from our second postulate of special relativity that it's moving at the speed of light. So we can write this as c times t. And the t here is measured from our reference frame. So we have this distance vector here. We can create another vector. How far did the craft travel? Well, that's the velocity of the craft times t, and that's again measured from our reference frame. Now we want to superimpose another vector, another distance vector, but this time it's measured from the person on board the craft. So she's on board the craft here, and she's looking at the light clock, but she's moving with the light clock, so the particle goes up and down here, and she sees no such triangular path. It just goes up and down like we see our own light clock, but it's also moving with a velocity c. So what we need to do here, we're going to superimpose the vector from the craft's pilot, or the train engineer. We'll call it a train because it's tradition. But we put a little prime there. So that's the reference frame from the individual on board the train. Now this should look nice to you because it is a right triangle. So we can invoke Pythagorean theorem, which is, if we square all these terms, this vector squared plus this vector squared is this vector squared, plus t prime squared equals c squared times t squared. So what we're going to do at this point is we're going to simplify it. We're going to divide by t squared, and we're also going to divide by c squared for every single one of these components. So this first term is going to look like that. The second term we divided by c squared, and we divided by, and I forgot to square this probably because it had the tick mark there. We're going to divide this by c squared, and we're also going to divide it by t squared. So we have t prime squared divided by t squared equals 1. C squared times t squared over c squared times t squared is 1. Great, so at this point, subtract this and move it over here. And what we're going to do is come up with a familiar expression. Take the square root of both sides. And then we're going to flip it. T to t prime equals the gamma factor. This is the gamma factor, which is the cornerstone of special relativity. Now, this can give you the ratio of the time as measured from u as to the time measured on board the craft. Another way you can think about this is you can just move. Let's see if we can do this. Move the t. Yeah, it looks good actually. T equals t prime over the square root. So if you're going 0.866 of the speed of light, that's gamma factor of 2. Well, the square root of 1 minus 0.866 over 1, and both of those quantities are squared. This fraction is going to end up being 2t prime times t. So that's pretty fast. But what that will mean is that if 1 second passes on board the craft, remember you're in the unprimed frame, you're looking into the primed frame, you're looking through the window, 1 second has passed inside of the craft. That will mean 2 seconds have passed for you, because you have this 0.5 in the denominator. V is 0.866, but the whole denominator ends up being 0.5. So 2 seconds have passed for you. Think about it. You look 2 seconds, tick, tick, tick tock, and then you look on board the craft, tick, 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 tick. So you're going tick tock, tick tock. You look on board the craft, tick tock, tick tock. Time is going slower for the person on board the craft, and that's that time dilation. The engineer of the train doesn't notice the passage of time because all internal clocks on board the train have slowed down. And so that's the principle of time dilation. And again, if you follow the mathematics where it's lead, it's a necessary result of time being the speed of light being a constant. Time must vary in order to maintain that consistency. So let's talk about the equation, this actual gamma function. So if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those aren't to scale, and this is c. So remember, this is the gamma function, and this is 1 minus v squared over c squared, and the x-axis here is going to be your velocity. The gamma function, if you graph this, it's going to look like this and like this and like this. And then here you get to 0.866, remember? And that'll be 2. So about right here, it'll go to 2, and then it'll just shoot straight up, bam! And it will never reach this asymptote. So the gamma factor is almost nothing for any kind of reasonable speeds, which we would be used to, and then once you get closer to the speed of light, it shoots up abruptly, and you're able to graph this function for yourself. So moving objects move slow. You can think of it like if it's moving fast, then the clocks have to slow down to almost compensate for that. Now, he sees the exact same thing looking outside of the window as you do looking inside of it. To him, your clock is going slow. So this presents an apparent paradox. However, as we will see later, this is not actually a paradox. The contraction of space and the fact that you're far away, I mean, it's confusing to think about, but it's a necessary implication of the mathematics. Thanks for watching.